Hi, good morning, all. Welcome to physics class. And today we're going to be continuing from where we left off last week, right? So last week this whole summer we've been doing what magnetism and electromagnetism. But more so, we ended class last week on the calculations part of transformers. And today, as a first question, we're going to do um, right. Well, we're going to do a revision question on on what we did last week. Just so everyone can get back on track, because we have a ton of calculations to do today. Right now, we have a little game to play as usual. We're gonna play the card battling game, right? Where one team, like two teams versus the other team in the card battles, and the winning teams get 20 extra points today. Right? Right, so let's get started, right? Let's go. So today's first revision question, and I want you to draw the diagram. I even put back the formulas you need and whatnot. And it's not just about doing back the question. It have some things, some new things that I need just to mention after we finish the question. So here we have a transformer. It have a left-hand side and a right-hand side. You'll notice everything on the left-hand side is it's kind of in a blue, and everything on the right-hand side is on a kind of red. So by now, provided that I did a little bit of revision, the left-hand side in this case is the primary side, and the right-hand side is the secondary side. Okay? So what you want to do in this particular case is find all the missing values. You have to find the current on the secondary side, the voltage on the secondary side, the power on the secondary side, and also the power on the primary side. Okay? So get started. Please, you have about I should probably give you a little bit more than 5 minutes because you have to draw the diagram. Take about 8 minutes to draw and get all four answers and to send the answers on the chat. Right? Answers have also already started to come up right now. I know the answers in some cases are coming up fast, but you gotta make sure and draw the diagram. So when you're revising, you have something. And I know there was a homework question. I'm really sorry about skipping the homework question, but you're gonna realize this question is basically a replica of the homework question, just different values. All right. So I really did forget to correct the homework, but if at the end of class, like if I finish everything I need to finish, we could go back and do the actual homework question. So I do apologize. Now, there is a kind of way to check if your answer is correct. In a perfect, I just giving people some advice, right? In a perfect transformer, like if everything is working perfect, but that's a kind of make-believe situation because nothing in life is perfect. But when you now start to learn about transformers, the assumption is, just for introductory purposes, it's perfect, which means when you calculate the power on the primary side, a circling it, and the power on the secondary side, the power, not current and not voltage, power. Power is supposed to be the same on both sides. So if your primary power and secondary power happens to be the same, well, then most likely you are correct. Like all the calculations were correct. But if the power on the primary side and the power on the secondary side are different at the end of your question, I think you should double check your working because that's a good way of leaving the exam room confident. Okay? Right? So for those who get in different answers for the primary power and the secondary power, check back your working. Something is off. We have about 3 more minutes. Most of this is going to boil down to cross multiplication. Cross multiplication. Right? And I'll show you a little kind of shortcut how to make life a little bit easier when sometimes you have larger numbers, right? So, like I said, I just don't want this to be a repeat, an exact repeat of last week. I want to give you a little bit of extra information on how to make the question easier for yourself. Anyway, 2.5 minutes. All right. Literally one more minute left. And I have to jump in and work out this whole thing. All right. I think it's time for me to jump in here. So I'm going to give you a little bit of shortcut tricks. One of the most annoying things about the transformers, right? In a lot of cases, not all the cases, huh? You see the values for the number of turns on the primary side and the value for the number of turns on the secondary side is usually be large values, like 1,000 and 8,000. Now, I know we're using a calculator, but still, dealing with 1,000 and 8,000, sometimes you're doing your calculations and you just stressed out and you just forget a zero. You know what to do, but you forget a zero. So what I usually tell students, what's going to happen according to the formula when you use it, remember, it's NP divided by NS. So remember the NP value is 1,000 and the NS value is 8,000. So when you put it in the formula, these three zeros is going to cancel out with those three zeros in any case. So what I will do, even before I start the calculations in my head, I will cross out these three zeros and I will cross out these three zeros. You can even do it in the exam. Like you can literally take your pencil or your pen and cross it out. The examiner will know that you're trying to make the work easier for yourself. So instead of using 1,000 and 8,000, just use 1 and 8, and you will get the same answer in any case. Okay? That will definitely make life easier. Also, we could try to predict what's going to happen in the question. Notice NS is larger. When I say larger than NP. What the N values tell you, it gives you an idea of what's going to happen to the voltage, not the current. It gives you an idea of what happens to the voltage. This transformer is called a step-up transformer. And when you say a step-up transformer, I must put in the word voltage here. Whenever you say a step-up transformer, and step up means to go higher or to get larger, that's the first thing that should come into your brain. It means that the voltage will get larger. You see, a lot of people mistake this. When you say step up, a lot of people say, but sir, are they talking about the current or voltage? No, by default in everyday communication, if you say you have a step up transformer, it means the voltage will get larger. But then you have to remember something I said last week. Current and voltage are opposites. Meaning that if voltage gets larger, your current is supposed to get smaller, and vice versa. If it's a step down transformer, right? If it's a step down transformer, that means the voltage will get smaller, but the current will get larger. So those things are things you need to keep in the back of your head as you do the calculations. But anyway, let's calculate the missing voltage first. And I will prove to you that everything that I just said will happen. To find the voltage, I'm going to use this portion of the formula. Remember, this portion, the V and the N's, the P's go on top and the S's go underneath. Current is the weirdo, meaning that he's upside down. The S goes on top for current and the P values goes underneath for current. You gotta remember that current is the odd one out. So using this formula, I'm just going, I don't have as much space on my screen as you guys, right, in your books. How much is VP? VP is 115. How much is VS? We don't know. That's what I'm trying to find right now. So I put VS. NP, I'm not going to put 1,000. I'm going to put 1 because we're simplifying it. And NS is 8. Doesn't that look much simpler than having 1,000 and 8,000? Immediately, you feel a little bit calmer. So let's cross multiply. I'm going to cross multiply this diagonal first. 1 by VS is VS. And we have to cross multiply the other diagonal. 115 by 8. I'm getting 920, right? And there's nothing else to do. That's the end of that particular part of the question. 920, and you had to put the capital V. Now you notice, because this side had more terms, the NS value was larger. It means the voltage was supposed to get larger. Did it get larger? I think so. It was 115. And when it came out on the other side, it was 920. So I know I'm on the right track. It was a step-up transformer. My voltage got larger. So most likely I'm correct, which means my current is supposed to get smaller. But anyway, for those who got this part wrong, take it down. And the next thing I'm going to do is find the current. Give you 20 seconds to take down what you need to take down. Right? Today is just going to be calculations right through. Right? And last week we went through how to cross multiply and whatnot and thing, right? So we should be okay. Right? A few people are telling me, yeah, they got it. Right? Some people sent very detailed answers, appreciated. Right. So like I said, we're going to find what now? The current. Now to find the current, we have two choices, right? Now, I mean, we have to use the red part of the formula, and we could use the V's or the N's. What I am going to do, I'm going to use this portion here, right? If you use the V's and the I's, you're going to get the same answer. It doesn't really matter, right? You just have to make sure and use the current part of the formula to find current. All right, so like I mentioned, just for recording purposes, I'll be using this portion of the formula to find the current. Okay. Start erasing. Let's use green here. NP, I'm using 1. NS is 8. It's on the screen there. IS, we don't know IS, so we just put IS. Do we know IP, the power on the primary side? Yes, 25. Look how simple that was. We just went to the formula, replace the letters with the particular values. And what will we do? Cross multiply, right? IS by 8 is 8 IS or IS 8, anyhow you want to write it. And 1 by 25 is 25. This 8 is a secret multiply, throw it across. You're going to get what? A divide. Let's divide that. 25 divided by 8 is 3.125 amps. 3.125. I know some of you might round it off to 3.13. I don't think you should do that because 0.125 is such a nice decimal. Remember, that's 1/8. So it's a real good idea not to round off nice decimals. Okay? Keep all three decimal places. It takes a little bit of experience and to know when to keep all the decimal places and when not to keep it. My advice is when you see familiar decimals, the ones that you learn in primary school, keep them. Do not round off. Right. Did the current get smaller? Yes, look at it. It was 25, and on the other side, it was converted to a mere 3.125. So this is a step-up transformer. In other words, to summarize, in step-up transformers, when the NS value is larger than the NP value, voltage will get larger and current will get smaller. Now, to leave the exam room smiling, let's calculate the power on both sides and let's hope we get the same thing. That's the only way we're going to know if we're 100% correct before handing up our exam papers. And the easiest way to calculate power, I showed you this last week, is to take the current on that particular side and multiply by the voltage on that side. So for this side here, what do you think? For this side is big. What's the current on this side? 3.125. And how much is the voltage on this side? 920. Let me multiply those two. 3.125 by 920 is 2875. And I put capital W because power is measured in something called watts. Let's calculate the power on the primary side. We're going to take the current and multiply by the voltage. Multiply these two because current by voltage for this side will give us the power on this side. 25 multiplied by 115, we got the same exact thing. Oops, that's a horrible color there. 2. So given the fact that this was a perfect transformer, if we're assuming it's an ideal transformer, power is supposed to be the same on both sides at the end of the question. And it is. So when I hand up my paper in the exam, I leave there confident. No way I getting anything wrong in that question. How much people, by raising their hands, got every single thing correct without my assistance? Right. Even if you didn't get it, once you understood what you did wrong, right? Right. Once you understand what you did wrong, still take it as a win. Now, with regards to significant figures, I hate significant figures. I will only use significant figures, like if the examiner forced me to write it as a significant figure. Most people here, I mean, the general rule is if something is difficult in an exam, you try to avoid it unless you have no choice. So if you want to put things in significant figures, fine. But you're just making life unnecessarily hard or difficult for yourself, right? There's no need to put significant figures, just put the values. Trust me, don't make life difficult for yourself. Two things, well, the main reason for that is you're not going to get any extra marks for that extra piece of fanciness. And you're more likely to make a mistake if you put it in significant figures in the long run. All right. Give you about 10 seconds. By now, everyone should be real close to taking on everything there. All right, let's go. Now, what's going to happen here, right, is that we're going to move on to a very, I'm not saying it's off the syllabus, huh? It's on the syllabus, but it's very, very rare. But it does come. So I have to prepare you for it. What about if a transformer is not perfect? If it is not ideal? In other words, there are different ways of saying a transformer is perfect. The examiner could say, hey, we have a perfect transformer, or we have an ideal transformer, or it's 100% efficient. All three of those things mean the same exact thing. Okay? It means the same exact thing. But sometimes it's not perfect, ideal, or 100% efficient. Like in this case, the examiner at the top of the question said, is 85% efficient. I have to show you how to deal with a case like this. First of all, everyone take down the diagram in detail. Draw it kind of big, take down all the information. In other words, make it look exactly like how I have it here. Right? When you finish, just raise your hands and we'll get started. Not more than 20 seconds again. All right, so let me show you how to deal with this question. Now it has a little bit of, how you say, SEA maths in this particular question. Let me explain what I mean by that. You have to know how to find the percentage of something. Remember, sometimes in primary school, they'll ask you to find 10% of something, or 50% of something, or 70% of something, or in this case, 85% of something. Right? So you'll see a little bit of SEA maths in the question. First things first. When they say it's 85% efficient, does this efficiency relate, are they speaking about the current, voltage, or power? I'm letting you know up front. This refers to the power and the power only. So when they say something is 85% efficient, you are not required to ask, hey, are you talking about the efficiency of the current or the voltage or the power? No, by default, it's always the power. And what does 85% efficient of the power mean? It means only 85% of the power will make it across. You know, usually in a perfect transformer, the power on the primary side and the power on the secondary side is the same. Like if you put in 800 watts here, 800 will appear on the other side. Reality is not so. Only 85% of the power will make it across. Now, here's the thing. Because this is not a perfect transformer, you see this portion of the formula here, you're never allowed to use it. You know why? This formula here only works for a perfect transformer. Only, so you're never allowed to use these formulas here when it's like 85% efficient or it's not perfect. You can use him and you can use him, but not this piece underneath. So if you wrote back this, cross it out. So you physically know that you're not allowed to use those formulas if it is not perfect, which is this case, it's not perfect. So how do you go about this now? Well, the first thing you have to do, right? You realize you have enough information on this side to calculate the power on this side. How do you calculate power on the primary side? Take current and multiply by voltage. Everyone do that for me. Calculate the power on the primary side, because even though it's not perfect, it's 85% efficient, you're still allowed to use the red and yellow formulas. It's still valid. So quickly find the power on the primary side. All I'm asking you once again to do is take the current and multiply by the voltage on the primary side. Send it on the chat. Send it. Easy stuff. Right, answers are coming up. Should be totally easy. Right. And we're supposed to get 960 because the instructions were straightforward. You're going to take the current and multiply by the voltage. 8 multiplied by 120. You're supposed to get 960. Don't forget your capital W. It stands for watts. Right. You're just taking 8 and multiplying it by 120. That's all you're doing. Now, here's the thing. In a normal, in a perfect transformer, what you would say is that if the power on the primary side is 960, well, then the power on the secondary side is also supposed to be 960. I know I'm saying the same thing over and over, but I know some of you are still processing it. This would be wrong. You know why? Because it's not a perfect transformer. Not all the power makes it across. It's like real life. If I give you $960 and tell you deliver it to the other side of the classroom, you really think $960 going to make it across? Nope, you're going to have some sticky fingers across there. Money is going to go missing, and probably by the time the $960 reaches the back of the classroom, it might only have $800. That's how life is. Things go missing all the time, right? So how do you actually calculate how much power makes it across? Well, this is where your primary school math comes in. Only 85% of it makes it across. So how do you find 85% of something? You say 85 over 100 because percentage is always out of 100. And you multiplied by the 960. You think you could complete that calculation for me? We're just basically finding 85% of the 960. And whatever answer we get is how much makes it across to the other side. You should be able to get it out from there. Super easy. Find 85% of 960. You'll get 800 and something, right? Well, obviously, I want to know what the something is. Right, one person, two people, three people have it correct. Right. I'm not responding to everyone, right? It's a lot of messages, but I am checking as much as I can, right? I'm checking, I'm reading, I'm doing what I can do. Right. And it's just a typing on the calculator, right? And so far, all the answers are correct, and I'm happy. Is 816. 816 watts. Okay? Easy stuff. Look at it. We basically almost there's a small problem with you wasn't supposed to find this. So let's cross that out, right? They're not gonna ask you to find it. That's not valid in this question. Great. So it's only one thing missing now. Now remember, we still can't use these formulas, the ones we cross out. So don't even dare look at them. We just have to find what? The missing current now, because we have the power on this side. The examiner gave us the voltage that was given to us. We just have to find the current. How do you find current? To find current, you just take power and divide it by voltage. Look at it. Remember last week I showed you how to use this? If you're trying to find current, the remaining part of the formula says take power. This line means divide. Power divided by voltage. Don't we have the power on the secondary side? Don't we have the voltage on the secondary side? Shouldn't we be able to find the current? I'm just asking you to take 816 and divide it by 480. And that will give you the current on that side. So you notice we didn't use the formulas we crossed off. Well, basically, we only used one formula, the red formula. Some of y'all might find this easier than a regular, boring, ideal transformer question. Right. So nobody's supposed to get this wrong, right? All you're basically doing to find the current here, you're just taking power and dividing it by voltage. 816 divided by 480. You're only using values on the secondary side because right now we're trying to find the current on the secondary side. So all the values must be secondary values, not primary values. 816 divided by 480, and we got a real nice number. We get 1.7 capital A for amps. Quick question. Is this a step up transformer or a step down transformer? I'll give you a hint. When you're trying to figure out whether it's a step up or a step down, you look at the voltage. Don't ask yourself what happens with the current. The voltage tells you whether it's a step up or a step down. Let me know in the chat, step up or step down. Right. It's a step up. Remember, well, a few minutes ago, we did discuss this in detail, right? It has to be a step up. A step up means the voltage will get larger. Look at it. The voltage was 120, and then it got larger when it came out on the secondary side. It starts off as 120 and ends up at 480. If the voltage got smaller, if it would be obviously a step down. All right, so once again, step up and step down refers to what happens to the voltage, right? So, and like I said, this is a very rare question, but it does come in the exam sometimes, the one where it's not 100% efficient. All right, let's take a little brain relaxer. Let's start we're doing the cards battle today, right? Oh, by the way, this here is the standings of all the teams so far. I know you all haven't seen it in a while, right? But I went through the whole week and all the missing points, I tallied it up, right? This is where we stand at the moment. The yellow team is still on top with 246, but the green team is slightly in the last place now. We're 183. And red is second and blue is third, right? So that's where everything is standing at the moment, okay? Right. So what's going to happen today? We're going to do our card shuffle thing here, right? The left-hand side belongs to the red and blue team. And of course, the right-hand side, you can watch the colors, belong to the yellow and green team. The winning teams today will get 40 points. So that would, whichever team wins, they can actually bump themselves up to first place. So on the blue and red team, we have beef pastel, aloo pie, salt prune, the lagahu, and soup, meat. Right? And on the yellow and green team, you have bun up roti, ole chips, evil bread and chana, bun palori, and chicken roti. Let's start the first battle. Let's see who wins. Lagahu versus bun up roti. Oh, I think the Lagahu is getting the advantage here. For bun up roti. All right, so the red and blue teams are currently in the lead. Let's have one more before we move on. It's Lagahu again versus the evil bread and chana from the other team. Let's go. Oh, I think the bread and chana is getting the advantage. Yep. Never doubt bread and chana. All right, so we'll come back next time and continue this battle, guys. So congrats to both teams. Both teams are on the same level at the moment. Right. Let's move on. All right. So the question is, I'll give you some time to write down, right? Let me talk a little bit, because if you're writing and talking at the same time, you're going to miss out on key things. Remember I said transformers are not ideal or perfect in real life. In real life, some of the power is lost. The power on the primary side is always larger than the power on the secondary side because, like I said, power goes missing. But why? Why does a transformer lose power? You need to know some concepts first of all. Right? Remember, a transformer works with current. Now, here's something you need to know. I know most of you all haven't done this topic in detail. Electricity. You just kind of briefly mention being introduced to it while we're doing magnetism and electromagnetism. So I'm just going to give you a little rundown. Everything has something called resistance, electrical resistance. You have electrical resistance. Every piece of wire, a brick, a piece of wood, plastic, everything has this thing called resistance. Even if it's the first time you're seeing this word, just know the symbol for electrical resistance is capital R. And what happens? Resistance is the enemy of current. You see, current, remember the symbol for current is the letter I. And let's put it here in case you forget. The symbol for current is the letter I. And current is measured in amps, capital A. You see the two of them, resistance and current, they hate each other. They are enemies. Current is like water. It's always trying to flow. You see, whenever you get shock, that means current is flowing through your body. Resistance tries to prevent current from flowing. So technically, resistance is your friend. The more resistance your body has, the less current can flow through your body when you are getting shocked, right? So resistance can actually save your life. But here's the thing. Resistance creates something called power loss. You see, when you see this formula in physics, remember don't mix it up with this formula. Remember, just now we use a formula. P is I multiplied by V. The two formulas look kind of the same, but this one has the letter R in it, and the I has a squared. This one doesn't have a square. In this formula, the power stands for power loss. It actually lets you calculate how much power is lost. Now, let's take a very simple thing, like a piece of wire, electrical wire. Transformers have electrical wires. Look at it. It have, in this case, red wire on the primary side and red wire on the secondary side. So obviously current is going to flow through those pieces of wire. Here's the thing a lot of people don't know, but you've actually experienced it before. Anytime you have a piece of wire and current is flowing through it, I put an I for current, right? Anytime current is flowing through a wire, you just have power loss. Power is being lost in the wire. That's bad, eh? Power loss is a bad thing because every time you lose power, that is money. It takes money. Power costs money. So if you're losing power, you're losing money, plenty money. You see, a piece of wire has a resistance. Remember, I told you everything has what? A resistance. When current flows through wire, you notice the wire does get hot. You know how I know you experience this? When you're charging your phone and your charger, which is made up of wires, if you ever crack open a charger and you must find wires inside of it, you will notice that your charger does get hot or warm when you're using it. There's a physics explanation for that. That heat that you're feeling is the power lost. That heat is not good. You're losing that heat. That heat doesn't do anything useful. It's just getting hot and being lost in the atmosphere. And there is a way to calculate the amount of power lost. You just have to take the current and square it and multiply it by the resistance. And that will tell you how much power is lost. Now, the bad thing about it, the larger the resistance of the wire, the larger the resistance, the more power loss it has. So here's the thing. When you're using a transformer, because a transformer is using current, right? And the wires have a resistance, there will automatically be power loss. which is what the first note is about. There are 4 ways a transformer can lose power, be not efficient. And the first is the resistance of the windings, right? And the other thing is this. When you're buying wire, anybody here ever went with your parents to buy wire in the hardware? Anybody here raise your hands? Ever went to buy wire? You notice it have different types of wire, different thicknesses. Some wires thin, some wires are fat, some cheap, some expensive. Quick question. Let me see if you all get the concept. When you're buying wire, do you want to buy wire with a small resistance or a high resistance? I'll repeat the question. When you go to buy wire, do you want to buy wire with a low resistance or a high resistance? Think about it and send your answer. This is very important because one day you're going to have to buy wire for your house, right? And it makes a difference. It makes a difference if your wire has small resistance or large resistance. You have to know which one to buy and which one is better. Send the answers. We have a lot of time to talk. Don't write down the notes now. I realize some of you all are just not answering. You're probably writing down the notes. Listen to me, please. All right, I'm going to give you the answer. I know some people are not too sure. You want to choose a wire with a small, well, another word for small resistance is low, LOW, resistance. You know why? If you do this calculation, I'm going to prove it to you in a little while. We have a whole calculation to this. The smaller the R value, the smaller the R value, the smaller the power loss. Because if you multiply something small by something else, and you'll get a small value because power is current squared multiplied by resistance. So you want to do your best, and this is always the case. Whenever you go to buy wire, you always want to buy wire with a small resistance, because small resistance means smaller power loss. And the less power loss you have, the better. Because nobody likes losing power. So it raises the next question. Why we just don't always buy wire with small resistance? You know nothing in life so simple, right? Which one you think more expensive? The wire with small resistance or the wire with large resistance? Which one you think more expensive? The one with small resistance or the one with large resistance? The answer should be obvious. Why? The smaller the resistance, the more expensive it will be. So it's not like you could just go in any hardware and say, hey, give me the best wire you have, the one with the smallest resistance. Yeah, the man will bring it for you. But when you see the bill, your eyes will fall off, right? So it all depends on how much money you have, right? The more money you have, obviously, the better wire you can get. Now, here's what a lot of people don't know, right? We're just talking, guys. Remember, it have thin wires. There's a bad space here. Well, we already, okay, down here, right? We have a thin wire, and here we have a thick wire. Oops, 1 second. I'm going to draw this one in red also. The thicker the wire, right? The thicker the wire, the smaller the resistance. So I used to get this wrong in school. I used to think if a wire thinner, it had a smaller resistance. That is not true. Thin wires have a larger capital R is for resistance. Thicker wires have a smaller resistance. That is why smaller resistance wires are more expensive, because it's made up of more material. It has more copper in it. So and like I said, I got that in school wrong for most of my life. I always thought the smaller the wire, the smaller the resistance, when it was actually the other way around. Don't think about it too much. I know some of y'all are asking why. It's not really necessary for CXC level. Okay, when you reach Form 6, you have to know why the thicker the wire, the smaller the resistance. So this here is the first reason why transformers are not 100% efficient, because when the current is flowing through the wires, there must be some power loss. Now, someone asks, is there any wire in the world with zero resistance? Because if there was zero resistance, then zero multiplied by anything would be zero. It would be so nice to have a piece of wire, a perfect piece of wire with zero resistance. Zero resistance means zero power loss. Unfortunately, guys, no such piece of wire has been invented yet. Believe me, scientists are working on it. They are working really hard right now to create a material or wire with zero resistance, but it just simply doesn't exist right now. That will be an amazing breakthrough in science when that is invented. Okay? Right. So I want everyone to take down only the first one. I want to discuss each one. Each one deserves a detailed explanation. I just don't want you writing it down and you don't understand the concept behind it. You won't remember it. But if you understand the concept, then remembering it is very easy. In fact, you'll never forget it for your entire life. Raise your hands when you finish taking on the first paragraph. All right. The next thing now is flux leakage. Okay. Now, what is flux leakage? Remember, all of these things we're discussing here is how the transformer loses power. Remember how a transformer works? Remember the last week or the week before, there was this diagram with a donkey, and we were executing the donkey because he did some kind of crime. Remember, I showed you that magnetic field lines from on this side would make it across to the other side, and the magnetic field lines would cut the secondary side to induce a voltage and a current on the secondary side. But the point is, I know I use plenty fancy words there, but the point is, the magnetic field lines, also called flux, right? They're called flux. Magnetic lines are called flux. For the transformer to work, magnetic lines from on this side must make it across to the other side. Now, in real life, there are billions of magnetic field lines, billions. Do you really think all the magnetic field lines from on this side will make it across to this side, and every single one of those billions of lines will cut the secondary side. Think about it. Some might make it, some might go too far and miss it completely. Some will go the other way. So not all of them make it across to the other side. Okay? Now don't get me, I'm going to give it this one time, even though I have the note on the next slide. The iron core allows, whenever you use an iron core, there's a greater chance that most of the lines will make it across to the other side exactly to where it's needed. It's not 100% perfect, right? But at the end of the day, not all the magnetic field lines from on the primary side makes it across to the secondary side. And because of that, it's not 100% efficient. Remember, magnetic field lines need energy. They need power. You can't produce those things for free. So it's like throwing away money or throwing away power in this case. That's the second reason why transformers are not perfect. They call it flux leakage, meaning leakage means some of the magnetic field lines are leaking to where it's not needed. Take down the second one. So there are two reasons you know so far that contribute to transformers not being perfect. All right. Coming down to the third way, something called eddy currents. Now, just to simplify this, but you need to know the explanation by the way, in the exam, right? When they ask you, why are transformers not ideal or why do they lose power? If you go in one textbook, you will see slightly different explanations. I mean, all of them trying to say the same thing. Don't get me wrong, they're trying to say the same thing. Some textbooks will say the same thing very long. Some, they'll say them very, very short. Here's my advice. You see these exact wordings? Memorize it by heart. And I guarantee you, once you memorize that by heart, you will get full marks. And I'm telling you, these are the shortest explanations you're going to get. It already simplified and summarized for you. Let's move to eddy currents. Remember, for a transformer to work better, it's not necessary. The iron core helps it works better. But it introduces a small little problem. Whenever you put an iron core inside an active magnetic field, remember there's a magnetic field here, right? What begins to happen? Small little currents inside the iron core begin to develop. Now, you don't want current in the iron core. You might think, well, that's a pretty cool thing. That's a pretty useful thing to put to have a current in the iron core. No. This current here, first of all, is not necessary for anything. It doesn't do anything useful. 1 second, guys. Just one. Oh. It doesn't do anything useful. I mean, it's current, it's just there, but it doesn't do anything useful. The person who discovered these useless currents developing in the iron core, because it's living in an active magnetic field. I think his last name was, I can't remember if his first name was Eddie or if his last name was Eddie, but he was the person who discovered that. Remember, everything has what? A resistance. And anything that has a resistance and a current flowing through it will have a power loss. So these eddy currents were flowing through an iron core, which naturally has a resistance. And that introduced a power loss in the iron core. So now, even though the iron core helped the transformer to work better, it introduced a very small problem. The eddy currents, which created some power loss in the transformer, right? But I know some of you are saying, oh, God, just take out the iron core. The iron core is one of those things that does more good than bad. It has more advantages than disadvantages. So that is why people choose to leave the iron core in the transform. Take down the third method, the third reason for power loss. You should be finished there now. Right. The last one, the fortunately for you, hysteresis. While it sounds like something complicated, actually it is kind of complicated. The examiner isn't going to, how you say, test you on it too much, right? The concept of hysteresis is this. If you put an iron core inside a magnetic field, won't the iron core turn into a magnet as well? Well, whenever you put iron close to a magnetic field, in this case, they're not even close to a magnetic field, it's inside a magnetic field. I had told you all that iron will eventually turn into a magnet. I think we did that on the first day of the summer classes. Do you think turning something into a magnet happens for free? No. The iron core will absorb some of the power from the system to change into a magnet. So now the iron core, which has more advantages than disadvantages, is absorbing or stealing power from the whole system so it can change into a magnet. That process is called hysteresis. Okay? take down what hysteresis is. Like I said, the examiner is not going to what? Test you too much in that. When they reach Form 6, you have to know what hysteresis is inside out. But for CFC, please remember my wordings perfectly. And when the question comes and says, hey, state and explain how a transformer loses energy or power, or why it's not ideal, you know exactly what to write in the exam, word for word. Okay? And you can guarantee that if your teacher does this topic for term, during the term, and you know you're getting tested for term tests, this question will come in. I can't imagine a teacher setting an exam on magnetism and electromagnetism and not bringing this exact question. It's a standard core question. When you finish, just raise your hands. I know your hands probably hurting from plenty right now. We'll take a small relaxer just now. We have another card battle. All right, so that should be more than enough time there. Yeah, let's go. Let's have a little card battle here. So I think, yes, it was, yes, that one. 4 versus 4. Let's have our next fight. Aloo pie versus chicken roti. Oh, I think aloo pie has the drop on chicken roti. Ugh. All right, so the left-hand team is winning so far. Ole chips versus beef pastel. Oh, I think beef pastel getting whooped. Oh, poor beef pastel. Well, I can't blame him. Ole chips is really tasty good. All right, so it's still even. Let us do one more. Let us do one more. I want to see if you can leave here with one without it being uneven. Salt prunes versus bread and chana. Oh, it seems that the green and yellow team is in the lead at the moment. All right, we'll continue that another while. So the next slide is going to be about, now that we know what causes loss of power in a transformer. Let's say you are hired now to reduce the amount of power loss. Like, you can't make it 100% efficient, but they want you to make the transformer better. Let's say that was your job. What would you do to improve the transformer? But don't worry, they figured it out about 100 years ago, but it doesn't make believe. How can we reduce power loss? Well, the first thing should be obvious. All transformers are made up of wire. The first thing you want to do is use wire that has lower resistance. Remember, lower resistance wire is more expensive, but at least you get less power loss. So that's I mean, it all depends on your budget. You might suggest to your boss that, hey, let's buy more expensive wire that has lower resistance. The boss might say, okay, if he can afford it. And if he can't afford it, well, hard luck. You just have to do with the cheaper wire. But that's usually the first thing they do. They use the best wire they could possibly use. The other one, remember I told you, in the iron core, small currents does develop. You call them what? Eddy currents. To reduce the eddy currents, you do something called lamination. Now, a lot of people probably don't know what lamination is. I'm going to draw a kind of 3D diagram here. Let's say this is the iron core. Let's say the iron core is a, well, I'll try my best to draw a shape here. I think you all can see the shape here, right? And what we're going to do is wrap the wire around it. So the primary side will get wrapped around what? This side. I'll use blue for the secondary side, right? Right. Lamination. First, sorry, I missed one thing. This here is a solid block of iron. It's a solid block of iron there, right? And you wrap the primary and secondary sides around it. Lamination is when you slice it up into smaller pieces. So it's like you have a real powerful knife and you slice it here. So it comes, I'm just taking this, I want to look at this piece here. So what you're going to do is slice the iron, right? And in between the iron, you're going to put an insulating material. So you have an alternate, in between the iron, the slices of iron, you're going to put insulating material, things that current cannot flow through. So it's like a sandwich now. Instead of just being bread, you're putting cold cuts in the middle. So it's iron and then something that electricity can flow through, an insulator. And then you put iron and then an insulator. An iron and then an insulator. So it's like a multi-layered sandwich that is not a pure block of iron. It's iron with slices of insulators in between. That is called lamination. Now, nowadays in the exam, they're not going to ask you to draw the laminated core. Lucky for you, the physics exam has gotten much easier over the years. You just have to be able to state the word lamination. But I wanted you to know what lamination was, okay? And when you laminate the core, it doesn't stop the eddy currents totally. Yeah? You can never stop the eddy currents, but it is reduce the amount of eddy currents. At least it is reduce it, right? Right? So you get less power loss, right? Now, the other thing you do, remember the iron core. Remember when we now started transformers, I told you you had to use an iron core and not to use steel or any other material. Iron cores, remember have this thing called hysteresis loss. Iron cores have the less or least amount of hysteresis loss. Never use steel. When you use steel or any other material, the hysteresis loss has become higher. Iron, soft iron, as some would call it. If you just say iron, the best way is to probably just say a soft iron core. Now, make sure and use the word soft. Don't worry about why too much, right? Just know that soft iron just have the least amount of hysteresis loss. Make sure you have all three things now, right? These things will reduce the amount of power loss. It will never completely stop the power loss, but it will reduce it. Right, raise your hands when you are finished. Oh, well, I want to make sure I'm correct. That homework question today, right? So we'll go back up in a little while and find the homework question. For those who are, eager to see if you are right or wrong. But we're going to try together, right? Take about 20 more seconds, and we're moving up to that homework question. Let me see. Some mistake here. Oh, yeah, I forgot a little L here. Material. Small error there. All right, let's get ready to see that homework question. Well, let's see if you guys have it correct. Yeah. What was the homework? I think it was this question here. Right, was this the homework question? Just raise your hands if this was the homework question. It should be the homework question. Okay, somebody says no. Was this the homework question? I think this was the homework question. Yes, right. People are saying yes. All right, great. Now, quickly, this is going to be a perfect this is just the homework question, right? So by just looking at this, it is a perfect transformer because last week we only did perfect transformers. Is this a step up or a step down? It's clearly a step down because you look at the kind of the n values, and this value is smaller and this value is larger. So if the n values are getting smaller, that means it's a step down, which means the voltage is supposed to get smaller. Now, this one here, I can't really simplify this one, right? I'm going to have to use the whole values, the 1250 and the 10,000, unfortunately. The most I could do is scratch out 1 0 here and 1 0, but that isn't going to make anything much easier, all right? So let's calculate the voltage on this side. Now, I know a lot of people didn't do the homework, right? And I did ask a few people on the chat if they did the homework. And, well, most people who I asked didn't do it. So you're going to help me out here. Use this portion of the formula to find VS, or the voltage on the secondary side. You have VP, you have NP, you have NS. Substituting the values, cross multiply. You shouldn't take too long to do that, right? Guys, and also when you're given homework, right? Please do it. I have a little problem with the Monday maths class. The circular theorem homework was given almost 2 weeks now. And I could safely say, because every time somebody accesses the homework, right? I don't know who's doing it or whatnot, but it gives me a counter. It could tell me, hey, 4 people try the homework, or 6 people try the homework. That class, the Monday class, has roughly 700 people in it, 700 to 800 people. And you know how much people did the homework? 6. So guys, I'm gonna have to put my foot down here, right? What I'm going to do, I'm going to do a check next week, right? I'm going to have to do a check, right? I know it's summer, but I can't have 800 people and only I think 6 or 8 people did the homework. That's a really, really low number. So here what? After class, everybody who's in maths class, stay back. I'm going to give you the link again for the homework, right? And then during class next week, well, throughout the weekend, right? I'm going to communicate with the parents. I can't call all 800, obviously, right? But I am going to sample call parents and ask if the homework is there. If the student has attempted it, if they have it in their books. Okay, I have to do a sample check. And I'm sorry to say, if you don't do it, like if you didn't check it and whatnot, I'm gonna have to put you out of the Monday class. Because you can't just come with your hands swinging out. I mean, I invest in my time. Some people actually doing the work. I want to make sure we leave here and you actually come out and you tested yourself and you actually learned something, right? So that's for the Monday maths class. Huh? And I'm going to send a message on the group as well. If it's not done, when you come Monday and you find yourself outside the classroom, because I put you in the waiting room, you know why, okay? So please stay back and get the homework for the Monday circular theorems actually started. I don't expect it to complete it, but a genuine start. Okay? That's my rules, and guys. And for those who know me, you know I will follow, right? So, all right. So we're using this formula here in green. I'll be using the green circle. I'll put it in green here. VP is 500. VS, we don't know. NP is 10,000. It's so easy when you have a value with so many zeros to forget a zero. I've fallen for that trap so many times in school. You get stressed out and you forget a zero. So make sure and count your zeros properly, okay? And NS, 1250. Cross multiply. VS by 1,000, 10,000, you hear me? I say 1,000, that's 10,000. It's 10,000 VS. And 500 by 1250 is 625,123. The 1,000 is a multiply. Oh, 10,000 becomes, I keep saying that, but how much we get in there? 62.5 volts. How much of y'all got that? 62.5 volts. Raise your hands. Raise your hands. 62.5 volts. All right. Right. Next thing you want to do is find IS. To find IS, well, we could either use the N. So yeah, we'll just use this. And let's call it a day. I can use the V's with the red or the N's with the red. Huh? Anyone will give you the same answer. Let's use this one. Right. Easy stuff there. Like I said, this is homework, so I'm moving a bit fast. Right? You're supposed to have this down already. Or something close to it. NP on NS. Where NP? NP is 10,000. NS, 1250. IS, we don't know. All right? We don't know. And IP, where's IP? It's 32. Now, here's the thing. It is a step-down transformer because the voltage got smaller. It was 500. Now it's what? 62.5. So it is a step down, which means we could kind of predict the answer for the current. What's going to happen if the voltage got smaller? Current is supposed to be larger. So when I do my calculations, if the current started off at 32, then my current is supposed to be larger than 32. Let's see if that actually happens. Let's cross multiply. 1250 multiplied by IS, right? 10,000 by this is 32 with 4 zeros. The 1250s are multiplied. Throw it across, you get what? A divide. 32 with 4 zeros divided by 1250. That's all. 32 with 1, 2, 3, 4 divided by 1250. I got 256 amps. How much people got that? 256 amps. Raise your hands, raise your hand. Right. Now to leave class confident, well, the exam room confident, since this is a perfect transformer, let's calculate the power on the primary side and the power on the secondary side. Remember, to find power, current multiplied by voltage. Current multiplied by voltage. Take the current and multiply by the voltage on this side, and take the current on this side and multiply by the voltage. And see if we get the same answers for the both sides. And if that happens, well, nobody can tell you you're wrong. You're leaving that exam room smiling, knowing that you're 100% correct. Finish it off there, guys. Finish it off. Guys, stay back. I know some of you are going to bust out the class and not even bother about the maths homework. Please stay back. Let me explain how to access the homework. I will send back the link and everything, and you can get started on it today, right? Circular theorems will be the hardest topic you have to do for CXC math. It's the hardest thing for a student to pick up on, right? Invest your time over the summer. Get it out of the way, right? Right. When I use the formula, take current and multiply by voltage, is 16,000 watts on either side. When I multiply these two, I still get back 16,000. Right? So you know you're correct. So how much people got the homework correct without my assistance? Like you were just waiting on me to show you you was correct. You were just waiting for my answers to match up with your answers. Right? Right. Right. So before we continue with the cards battle, right, to see who ultimately wins, right? We still have some time. Let me just show you guys, send back the link for the homework, right? The maths homework I'm talking about for the Monday maths class. That's super important, right? Right. So for the Monday maths, when you all go to the page with the lesson with all the recordings, I send them back the link for the recordings, right? It's on the chat there. You will see the Monday maths class, right? You will see the circle theorems game here. It's better if you use a PC or a laptop. Try not to use a phone for this one. It's too small on a phone. You're not going to be able to see all the information. So when you click on the circle theorems game here in the Monday maths class, don't click download. You're clicking run game. Just run the game, right? And all the questions will start to load. You have to defeat the monster and whatnot, right? It's really, really simple. Now, the one thing that's going to happen, you have to read the instructions in the questions, right? So you could submit your answers. Try your best. If you get it wrong and you lose, don't just give up and say, sir, you can work this out for me. No, that's not how it works. You keep trying it until you get it correct. Because believe me, if I just give you the answer, you're not going to learn anything. It's like a real game. When a game gets hard, you don't call the developer of the game and ask him how to pass the game, right? You keep trying it. And by keep getting it wrong and keep trying it over and over, you're going to eventually get it correct, obviously. And you will fully understand it of it. All right, guys, so please get this done over the weekend because Monday is the maths class and you want to come in fully prepared and not end up in that waiting room, okay? Right? I will do my spot checks this weekend with all the parents and whatnot, whoever signed, okay? All right, so let's continue with the game, the card game here, and let's see who the ultimate winner is, all right? All right, Alupai has won. Alupai versus Evil Bread and Chana. I think Alupai going through there. Oh no, the red and blue team has the worst hero left, me. I think I'm gonna end Elixir, so. Oh no, sorry, red and blue team. Sorry to let you down here, but it seems that I'm not a good fighter, just like in real life. All right, with that in mind, guys, today's winner is the green and yellow teams. Okay, so the green and yellow teams. Let me just update the points here. The green and yellow teams both get how much points we said? It would have been 40 points. I think yellow team is still winning. So yellow team is still in first place. Green team third. Red second. And blue team, unfortunately, fourth place. All right, guys, that's pretty much it today. Thank you for sticking it out. And guys, don't forget me about the homework. It's for your own good. The maths homework. Please get it done over the weekend. Okay? Take care, guys. Have a good one. All right. For those who are, I know some of you are genuinely trying the homework, right? The maths homework, right? Let's say that you're genuinely stuck on the question. Now, I don't usually recommend this, right? If you know you tried that question like 5 or 6 times and you real bust your head on it and you still can't get it out, here's your last resort, right? You screenshot the question and you upload it to GDP or Gemini or whichever AI, right? But you just screenshot the question and it will work it out for you. Now, I'd already like telling people to do that if they're not trying. You know, some people will just say, I'm just going to use AI to work it out and just get my answers. I mean, anybody could do that without me suggesting it in any case. But obviously, you're fooling yourself if you do that. But if you know you really, really tried, you genuinely tried it many, 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 many times, and you just can't get the answer, only then I would recommend it. You upload it and you will get the answer and you'll see why you're wrong, right? But that's our last resort. Okay. So, and of course, if AI genuinely can't get it on, which I doubt, well, then, okay, fine. If you WhatsApp me in that case and you show me a general, like, you already explained to me that you really, really tried and what you tried, like you explain what you tried and thing, I will say, all right, I will give you some assistance in that case. Okay. But the aim is, I have this, when you WhatsApp me, you have to explain to me or send me real proof that you tried the question to the best of your ability. Because you can imagine how it is on my end, right? Where people tried halfway, they just tried one or two times. And the first thing they do is just, WhatsApp me for help without any proof that they really, really tried it. Obviously, in that case, I'm not going to take you on, right? So, which is fair, right? So keep that in mind, guys. Before you WhatsApp me, make sure you send real proof or an explanation of what you tried to really prove to me that, hey, I'm already trying on my end. And I will help you in a case like that. Take care, guys. Have a good one. You don't need to send anything after you do the homework, right? I will do my spot checks and whatnot. All right. Once again, for those who are having problems accessing the homework, remember, I sent the link to the recorded. I want to show you exactly what I am doing. So you're seeing my screen, right? I'm sending back this link for this page. I'm just showing you what is happening. All I did was go to the page. I found Monday Math, and you see the link over here for the game. Now, this is literally all I'm doing. I'm going to take my mouse. I'm just clicking on this. This is all, there's not much else I could do, right? So if it's not working on your PC, you have to probably check the settings on your PC. But you can look at me. I'm just clicking on it. Bam. And it goes to this page. If you scroll down a little bit, you will see run game. All I'm really going to do is click on run game and it loads. That's all you have to do, right? So if that doesn't work, but then the issue is with your PC, like something is wrong with your PC, or in a case like that, you can use your phone. But like I said, your phone screen might be a little too small. You might have to strain your eyes a little bit to see the questions, right? So try your best to use a PC or a laptop. Take care, guys. Have a good one. I'm out.